Hello, everyone, and it's so fantastic to see all of you in person finally at AWS Summit. Welcome to Resilience Strategies to Level Up Your Workloads, and my name is Rada Stanic, and I'm a Chief Technologist at ANZ here at AWS. We have a very packed agenda for the next 30 minutes, so I hope you can stay with me and take as much of this knowledge as possible. We will start nice and easy with some of the key resilience concepts, establish some definitions and how we differentiate high availability, disaster recovery. We'll then talk also about the importance of understanding fault isolation boundaries in the context of AWS Cloud. We'll touch on static stability and how it's useful when we consider resilience architectures. And then we'll get into the key part of this session, starting to talk about multi-region resilience, fundamentals to consider, and go through some architecture patterns that you may find helpful. We'll then wrap up by talking about finding the unknowns in your resilience architectures and also how to build in extreme automation. I'll bring up two exciting services that can really help you build resilient workloads in your cloud environment. And then I'll leave you with some final thoughts that you should think about as you go into your own organizations and look at resilience strategies to improve your workloads. So let's talk about some of the key concepts. First of all, what do we mean when we say resilience? Resilience is really the ability of the system to continue to operate during the failure, where that failure may be induced by load, attacks, or other failures, and to return to operations quickly. And quickly means within the boundaries and targets that you define as part of your business continuity procedures. When we talk about resilience, people sometimes use terms high availability, disaster recovery interchangeably. So I just wanted to level set the scene and basically define what do we mean by high availability and what do we mean by DR and how we measure them. So high availability is resistance to common failures through design or operational mechanisms, and it's measured in nines. I'm sure you've heard availability of 5 nines, 3 nines, and I'll show you shortly what that translates to. When we talk about disaster recovery, we really talk about the ability of the system to return to normal operations within predefined targets that are specified by your business continuity processes. And those targets are measured in what we call RTO and RPO, recovery time objective and recovery point objective. So two distinct concepts and measured in very different ways. And we also talk about resilience, and this is something I will emphasize strongly through today. We also talk about this notion of continuous resilience. So it's not that you design a workload and you leave it hoping that that's how it will behave, but you test. You test the technology stack, and you also test your operational teams to make sure that they know how to respond in case of failure through things like game days. And finally, as part of resilience posture, you also might be required to look at things like supplier contingency and exercise any portability plans if you need to do so. So the famous nines. I just touched on high availability and said we measure it in nines. So does it mean that you need to always design your system to be available for 5 or 6 nines? Absolutely not. You look at the criticality of your system and what is the maximum sustained time that that workload can afford to be down. And if you can't afford more than, let's say, a second of a downtime per day, then you really need to look at designing for 5 nines. If on the other hand, you can tolerate 14 minutes of downtime, that's maybe all that you need is a 2 nines availability. Now, I will say this 2 times through my session. I know there is a lot that gets said in 30 minutes, and there are 2 distinct points that I really want you to take away from today. And this is that first point. When we say at AWS, let's build a modern, resilient architecture, what do we really mean by that? And what are the characteristics of modern resilient architecture? Their ability to have extreme automation everywhere. It is also ability to establish continuous resilience practices and through techniques of chaos engineering, test and ensure that your system will always respond in the way that you are expecting it to respond. And finally, it's about having integrated observability and not just the infrastructure layers, but applications themselves. And if all of this is starting to sound a little bit daunting and you're thinking, that's a lot, we are here to help by giving you managed services that actually do a lot of heavy lifting on your behalf. And I will explain this in the very last part of my session. Another important point, if you've had any exposure to AWS Cloud, you know that we always say security is a day zero job. And then we also say that we have this shared responsibility model where AWS and our customers and partners share the responsibilities of how we build in security. It is exactly the same for resilience. The easiest way to remember, AWS is responsible for the resilience of the cloud, meaning underlying infrastructure, compute, storage, databases. And our customers, you, are responsible for failure management, change management, and the actual workload resiliency. And again, do not think that you have to do it all on your own. We give you best practices, artifacts, and we actually have very well-defined, well-architected framework where your friendly solutions architects come in and help you assess your workload resilience before you take it to production. Okay, so moving along to talk about some key concepts before we dive deeper into the architecture patterns. Fault isolation boundaries. How do we define fault isolation boundaries in AWS Cloud? There really are three: the concept of regions, availability zones, and partitions. And it's important to understand what they are because they will impact how you design resilience of your workload. A region, it's a physical location anywhere in the world that consists of multiple availability zones. For many years, we had Sydney region, and just recently, we've celebrated launch of Melbourne region, giving us a lot more options in terms of fairly low latency infrastructure available to us here, and Auckland is obviously coming in a not too distant future. And then we have availability zones. Typically, a region would have 3 to 5 of those, and availability zone is one or more data centers that are completely separated by distance. They have separate power, networking infrastructure. They have no common failure points. And finally, we have partitions. We have 3 of those that separate our commercial, government, and China region clouds. Also, when talking about resilience, very often you need to understand what is the control plane and what is the data plane and how they impact various failure scenarios. For any of you that have done any networking and have played with or worked with routers, you know that routers have control and data plane. Control plane tells any router how to send packets across the internet, what's the next hop, what's the destination. And data plane is the actual packets traversing the internet and carrying the useful information. It's that same analogy that we have with AWS services. Control plane allows us to create, update, describe resources. It's creating an elastic compute instance. It's creating an S3 bucket for object storage. It's describing EC2 instances. That's what a control plane is. It's very low in volume when it comes to traffic, but has fairly complex dependencies. When it comes to data plane, it's a higher volume of traffic. It's actually day-to-day business of that resource, sending packets between EC2 instances or putting an object into an S3 bucket. And it's simpler with very fewer dependencies. Why is this useful? It is useful in understanding different AWS service types and how they actually operate and what are their own individual fault isolation boundaries. So again, we have 3 types of services. They are zonal, regional, and global. Zonal services operate within the bounds of an availability zone. But more importantly, they fail within an availability zone. So if I have an elastic compute instance and it fails in one availability zone, it doesn't impact what happens in the other availability zone. The same goes with things like relational database, like RDS, and so on. And then we have regional services. These are the types of services that AWS has created to basically allow you, our customers, not to focus how these services map to availability zones, and they present themselves as a single regional endpoint. Think about S3 for object storage. Think about simple queuing service, and also our database like DynamoDB, NoSQL database. And finally, we have global services. Global services have single region a control plane, and they have global data plane. Again, those are things like identity access management, Route 53 for DNS resolution. So now that we have some of this context, we're building up that sort of critical mass of points and knowledge to go deeper into resilience considerations. Before we head into architecture patterns, I want to touch on the importance of static stability as a way to enhance resilience of your workloads. So again, how do we think about static stability and what it is? It is actually the ability of the system, whatever that system is and however complex it is, to operate in a static state without a need to make any changes when the failure happens or when we experience temporary unavailability of any specific dependency for that system. And again, there are 4 different categories: preventing circular dependencies. I'll show you an illustrative slide on that soon. But it's also doing things like pre-provisioning capacity. And I'll just pause a little bit here and explain what we mean by pre-provisioning capacity, because you may be questioning and thinking, isn't there a whole point of the cloud to have auto-scaling on-demand capacity? So why are you talking to me about pre-provisioning capacity? All those things are true. But let's say you have a workload that operates across 3 availability zones, and something happens to one of those, and suddenly you find yourself with 33% of your fleet of instances down. Now, auto-scaling will kick in, and the new instances will be spun up, and our load balancers will take care of sending traffic to healthy instances. So all of that will happen without any manual intervention, but it takes time for new instances to come up to running state. So basically, if your workload is of such a business criticality that you can't afford even that time that it takes for new instances to kick in, then it's very useful to have some pre-provision capacity so that you have that seamless experience if failure happens. So just wanted to touch on that as an example. The other aspects of static stability: maintaining the existing state, local copy of data to remove the dependency on other subsystems, and also eliminating synchronous interaction. You'll hear me a lot today about synchronous versus asynchronous. But basically, to start with, think asynchronous is good. So a couple of examples that I mentioned on static stability. We have a user making a request to system 1, which has dependency on system 2. If everything is working, user will get a response. But what happens if our dependency experiences temporary failure? It goes down, then the user will not be able to get response. And then what happens when we look at our 9's availability, the entire system availability goes below the level of the high availability of each individual system. So we obviously want to prevent these scenarios from happening. One of the ways to prevent that is to implement asynchronous communication and asynchronous flows. So one of the ways of doing that is to keep a local copy of data in system 1 to be able to deal with these transient failures. It could be a push or a pull model, but if you do have local copy of data, then if something goes wrong with system 2, it actually will not impact availability of system 1, and the user can happily get the response to the request that they've made. Okay. Hopefully this has made sense so far. We've gone through concepts, we've gone through some definitions, we talked about some important things like how we classify services, what's the meaning of fault isolation boundaries, and hopefully also thinking on whether static stability is something you need to consider in your environment. Now we're going to go through some patterns and considerations for multi-region design. It's only timely and appropriate to talk about that, given that we have Melbourne region available to us. Before we head into multi-region, I want to remind you all of just how much is possible with a single region multi-availability zone design. A lot of customers that I work with have exactly this kind of architecture. They might have a workload. I'm here just showing compute and database layer that spreads across two availability zones. And all those things I just described when I talked about static stability apply here. If something happens to one of my availability zones, load balancer and autoscaling will take care of those failures. Also, if something happens to my primary AZ here, the standby RDS in my database tier will immediately take over, so that's a failure scenario taken care of. And then potentially, we can use a third availability zone to store some backups and use it for disaster recovery procedures. So why am I spending time on this slide? I'm spending time on this slide to tell you that there is so much you can do with just multi-availability zone, single region patterns. And in some extreme scenarios, you may need to consider multi-region. And let's walk through those and why and when would you implement multi-region. One of the key things to consider, and you'll see it from the patterns, is how do we replicate data from one region to another? Okay, so I warned you in the first part of the presentation that there will be 2 points where I'll call for your attention and hopefully inspire you to remember something from this and consider it. First one was around the characteristics of modern resilience architecture, and here is the second point. These are the 4 key fundamentals to consider before deciding whether multi-region is the right scenario for you and your environment. The first fundamental is understanding the business impact of your workload. Of course, you understand your workloads. You design them, you know how they operate, and you have that clear understanding. But it's useful to step back and map your workloads according to their business criticality. Having 3 tiers is pretty good, and you map them according to the desired RTO and RPO that you must meet in case of some failures or interruptions in your environment. And once you have that clear view, you will very quickly see that not everything is a top priority, not everything is mission critical, and those things that are, they become strong candidates for the multi-region. The second point, and my favorite, maybe because it's in my humble view the most complex to solve, is understanding the data. How are you going to keep data synchronized between the regions? And a useful analogy to use here is that one that's used for most distributed systems, the CAP theorem. CAP theorem is based on an assumption that at any given point in time, for any distributed system, you can only meet 2 of the 3 key characteristics, those being consistency, availability, and partition tolerance. Given that we're talking about multi-region design, then partition tolerance is a given, which means we need to show some flexibility around consistency and availability. And this is where my discussion around synchronous and asynchronous replication will come in play as I discuss the patterns with you shortly. The third fundamental point to consider is, do you have any dependencies? And those dependencies are, let's say you designed your workload for 5 nines high availability. You designed it for near zero RTO and RPO targets. But what if you have dependency of an on-prem system that's a single point of failure? Your system then becomes as strong as the weakest link in that end-to-end architecture. Or what if you have dependency on a SaaS application that may be running in AWS cloud or somewhere else? So understanding dependencies is key. And last but not least, it's operational readiness. So do I have, or do you have, the correct services that you want to use in the region where you want to expand? And also, are you ready in terms of your permissions and policy controls? So once you have analyzed those 4 fundamental principles, you will hopefully have a clarity in terms of whether you need to consider multi-region design for your workload. Now, there are really 2 macro patterns, active-passive and active-active. Active-passive is great when you need to establish disaster recovery procedures. One region is active and the other one will be used in case of disaster recovery. Why would you want to do this? Maybe because of regulatory, that's the most common requirement. Maybe the regulatory bodies are requiring you to do this, and the availability zones and what I was describing in the very beginning isn't sufficient. So that's when you would consider active-passive. Active-active is a pattern that's useful for extreme high availability, for really low RTO, RPO, and again, regulatory requirements. And on the next few slides, I will dive deeper into some of those patterns. This is not an exhaustive list, but some examples to inspire you to think and consider that if they may be applicable to you. In this particular case, we have what's called a case of regional sharding. We are simply mapping users to their nearest region, and we are supporting use cases such as global expansion. This is nice and easy because there is no need to implement any replication here. We simply map users to be serviced in the region that's closest to them. In this next case, we have what we call single writer and multiple readers. This is a case where we want to support workloads that are extremely read intensive. So we're writing all of our transactions to a single region, region A in this particular case, and we are reading from both regions. Also, you will notice here that we're talking about asynchronous replication because, for the sake of an example, we're saying that eventual consistency is sufficient. So this could be a really good pattern if that eventual consistency in terms of keeping data in sync is sufficient for you. In the next example, we have what you've just seen, but it's now strong consistency as a requirement. So basically, what we are saying is we can't send a response to the end user without being sure that transaction has been committed to both regions. And I told you in the beginning, if you recall, that synchronous should be avoided because it introduces additional latency and your workload, your applications may not be equipped to deal with that additional latency that will be induced by having to replicate transaction before we send a response to a user. But in some cases, this might be sufficient and might work well for you. Now, you can see this case of dual writes, and you see the magic point, no replication here, seems nice and simple. And every time when something that you use to solve a relatively complex problem in an architecture looks too simple to be true, well, usually is. Complexity has to be dealt with somewhere at some point. And here we are dealing with complexity on the client side by building in logic on the client side so that the replication doesn't have to happen between the regions themselves. There is an additional thing that you need to consider here, and that's the issue of idempotency. Basically, what happens if through some transient failure, one transaction gets committed twice? Can your backend logic and your software deal with that duplicate transaction? So again, could be a good choice, but something to think about. And finally, the last pattern I want to call out, something I see frequently adopted and used by our customers, is this one of multiple writers, multiple readers, but leveraging managed services such as DynamoDB to do asynchronous replication at global scale. This is a really good pattern because it has built-in mechanisms to deal with things such as conflict resolution through last writer wins capability. Now, this is a little bit theoretical, you might say. So that's why I wanted to show you an example of a real customer that's implementing this in a real life. It's a financial services industry customer, Vanguard, who operates out of 3 regions. And what they've done, what they patent for multi-region design, which also includes follow the sun model, is they always have one region which is primary or a hub. And then all of the write transactions get committed to that hub region, while the others provide fast local read access. They've built in a microservices layer to basically control how the replication to the spokes happen. So what happens when the traders start to work out of Australia as the follow the sun model kicks in? Australia becomes hub. Microservices make sure that all writes happen in Australia, and it replicates transactions to the spoke regions. They also use DynamoDB, but DynamoDB gets told by microservices which region is primary at any given point in time. So again, all these things I talked about are things and patterns that our customers use today on a global scale. So as we try and wrap up and come to the end of this presentation, I really want to draw your attention to two exciting services that can make your life so much easier and simpler as you level up the resilience of your workloads. Those are the finding the unknowns and the extreme automation. So just briefly, chaos engineering. There really is nothing chaotic about chaos engineering. It's a scientific method which assumes that you always know what you're expecting from your system if failure happens. So by running chaos engineering tests, you're verifying that your system will respond in the way you expect it. So you have hypothesis, known state, you run the experiment. If you get the result that you expected, it's fantastic. If you don't, you improve and you get to the state where your hypothesis is true. A few years ago, I remember Netflix coming to a stage of reInvent and talking about the teams of people that they have to implement chaos engineering. Now, any small organization can do this because there is a service called Fault Injection Simulator that allows you to do anything from shutting down EC2 instances, databases, injecting latency, increasing memory, CPU load, and many more activities than what's listed on this slide. So take advantage of this service to perform chaos engineering in your own environment. And last but not least, my favorite service in the resilience universe, AWS Resilience Hub. It just does so much for you. So with Resilience Hub, what you can do is you can onboard your application by using either CloudFormation or Terraform. You onboard your workload, you specify the RTO and RPO targets that you're hoping to achieve, and then the service will perform an assessment. And it will tell you, yes, you can meet these RTO, RPO targets, that's great. Or it will tell you, no, actually this RTO and RPO will not be met with the architecture that you have, but here are 3 recommendations that you need to look at to lift the resilience of your workload. And the best part about it is also it's going to give you estimated costs so you can choose wisely which option is the best for you and your own environment. Once you've decided on which option you want to use to improve the resilience to meet those targets you have, you can actually take action right there and then from Resilience Hub through its integration with Systems Manager to deploy those recommendations through the operating procedures they are given to you. Finally, Resilience Hub also integrates tightly with Fault Injection Simulator, so you can also do chaos engineering from that single environment. And finally, why do we call it extreme? So I just justified why do we call it automation. We call it extreme automation because ideally this should be part of your CI/CD pipeline. So hopefully, what I said earlier in the presentation, please don't be overwhelmed when I say modern resilience architecture involves extreme automation, integrated observability, and finding the unknowns. I've just given you 2 fairly straightforward answers on how to achieve 2 pillars of that architecture. So, in conclusion, what would I like you to take away from today's session? I would like you to really think about resilience in the context of those 3 pillars I just mentioned. I'd really also like you to remember those 4 fundamentals before deciding to embark on the multi-region patterns and deployments. Just because we have second region here doesn't mean that everything has to be multi-region, but we have flexibility to embrace it and improve our resilience posture if we need to. And finally, I'm sure it's obvious to you by now, multi-region design is primarily a business decision because of the cost associated, because of the ability to meet targets as defined by business continuity procedures, and only secondary, it's a technical decision. So just like I talked about improving your resilience workloads and leveling up your workloads from a resilience point of view, don't forget to visit Skill Builders Library in order to level up your own cloud skills. There are lots of useful resources there. And finally, thank you so much for choosing your time today to spend it with me in this session. I hope you've learned something that you can take away. And please complete the session survey in the app because we love hearing from you and what you thought. Thank you very much and enjoy the rest of your day.